Hi everyone, my name is Amitesh, and in this video I'm going to talk about the beautiful derivation of the formula for solving a cubic equation. Now generally in school, people are taught the quadratic formula and maybe how to solve quadratic equations, how to derive the quadratic formula, but people are generally not taught the derivation of the cubic formula or even what the cubic formula is. And part of the reason is that the cubic formula is quite a complicated, maybe ugly looking formula, but the derivation of the formula is really beautiful. And that's the goal of this video, to show something that many people aren't necessarily exposed to. Even I, as a professional mathematician who's been doing math for so many years, I haven't seen the derivation in depth until recently. And since I've seen it, I want to show it to you because I really love it and think it's so exciting. And I hope you love it too. So let's just dive right into what we're going to do. So we're going to start off with a cubic equation, which is an equation of the form x cubed plus ax squared plus bx plus c equals to 0, and we want to find a formula for x, the solution to the equation, in terms of a, b, and c. Now because it's a cubic equation, you generally expect there could be up to 3 solutions. And we want a formula for the 3 solutions in terms of the coefficients a, b, and c. And what we're going to do is, the first step of the process is we're going to explain, so I'm going to give you a roadmap before we dive into it, just to give you an idea. We're first going to explain, so step 1 is why it is sufficient to solve a depressed cubic. Okay, why it is sufficient to solve a so-called depressed cubic, and a depressed cubic is an equation of the form x cubed is equal to px plus q. Okay, so in other words, x cubed minus px minus q is equal to 0. Okay, so we're going to explain why it's sufficient to solve this kind of equation where basically the x squared coefficient is 0. Okay, so somehow we've transformed the problem to solving these equations where we don't have an x squared term. Okay, now even here it's still not that easy, but at least we've reduced, one coefficient we've taken out of the picture. That's step 1. And step 2 is we're then going to explain how to solve a depressed cubic. Okay, so how to solve a depressed cubic. How to solve a depressed cubic. Okay, now what I'm going to do is I'm actually going to, even though I've said this is step 1 and step 2, I'm actually going to start with step 2 and explain how to solve a depressed cubic, and then I'm going to conclude by saying why that is sufficient to actually solve any cubic equation. And actually that's not very difficult. Okay, so the difficult part is solving a depressed cubic, and explaining why it's sufficient to solve them to solve a general cubic equation is the easy part. Okay, so let's first start off with depressed cubics and explain how to solve them. Okay, now one quick comment before I do that is, in this equation you notice the x cubed coefficient is 1. Now that's not really a restriction, because even if the cubic equation you had some coefficient of x cubed like 5 or something, you could just divide the whole equation by 5, and because it's equal to 0, you'd get another equation with the same solutions where the coefficient is now 1. Okay, so you can assume that the x cubed coefficient is 1, it doesn't change any of the methodology. Okay, so let's first start off with depressed cubics. Okay, so that's going to be step 1. We're going to explain how to solve a depressed cubic. And this is a beautiful trick. It's a very simple and elegant trick, and I find it very beautiful. I love it. And we're going to talk about it. So I believe it was discovered by Ferro and Tartaglia, and it's named Cardano's formula. So there's some history behind it. I'm not going to repeat it because I don't know all the details, but it's on Wikipedia if you'd like to take a look. So let's kind of start off with the depressed cubic. So depressed cubic is an equation of the form x cubed equals to px plus q. Okay, so p and q are constants here. Okay, we want to solve for x in terms of p and q. So this is the beautiful trick. Okay, the trick is the following. What we're going to do is we're going to introduce 2 new variables u and v. Okay, so we're going to introduce 2 new variables u and v. So introduce u and v. So these are variables, and set x is equal to u plus v. Okay, so all we're doing here is we're just saying that we're going to write x as u plus v where u and v are variables. Okay, so u and v have some relationship to each other. They add up to give x, and now we're going to see what happens to this equation. Now, I'm not going to pretend this isn't something extremely creative. Okay, we'll see that this actually solves the problem, but it took a long time for human civilization to come up with this. Okay, so it's a very deep idea, but it's very simple too. And that's what math is beautiful. You know, simple ideas can be very deep. So let's do that. So we set x equals u plus v. What are we going to get? So we substitute. Okay, we're going to use the binomial theorem. So we're going to get u plus v cubed is equal to p times u plus v plus q. So remember, p and q are constants here. U and v are the variables. So we're going to try to find out what u and v should be. Okay, that's what we're going to do, and then we get x. We get the original x by just adding them up. So we've got this. Okay, let's kind of like simplify this. So u plus v cubed is going to be u cubed plus 3u squared v plus 3uv squared plus v cubed, and that's going to equal to p times u plus v plus q. Okay, so I've here used the binomial theorem to find u plus v, the whole cubed. I have videos on that in my channel, so if it's uploaded, check them out. Links will be in the description. But you get this formula and you've got this. Okay, so we want to find out what u and v are. Now, what we're going to do is we're going to observe the following. Okay, so I'm going to, first of all, I'm going to collect. I've got a u plus v there. Let's see if we can get a u plus v on the left-hand side. So we're going to have u cubed plus v cubed, and we're actually almost there. Okay, so it's just one more step. U cubed plus v cubed, the 3u squared v plus 3uv squared, we can factor out a 3uv from that, right? If you factor out a 3uv from that, you get 3uv. So I brought the v cubed over here to get u cubed plus v cubed, and we get 3uv times u plus v is equal to p times u plus v plus q. All right. So here's what the method is. Okay, so here's what Cardano's method is that we want to now, instead of solving this equation, we can observe the following. If we can find u and v, right? P and q are the coefficients of the original equation. Okay, so they are fixed in the problem. Now, if we can find u and v so that the 3uv matches up with the p, right? And the q matches up with the u cubed plus v cubed, then we'll have a solution, right? Because if we know that 3uv is p and u cubed plus v cubed is q, then this equation will be satisfied. So now we just want to solve for u and v in a different equation, okay? And the equation is the following. We want to solve for u and v with the following two equations for u and v, and the equations are going to be 3uv is equal to p, so 3uv is equal to p, and u cubed plus v cubed is equal to q. Okay, we want to solve for u and v. So we given p and q, we want to solve for u and v in terms of p and q, and then we add them up, we get our x. And that x will be in terms of p and q, and that will be our solution to our depressed cubic. Now we'll get up to 3 solutions, but let's first kind of figure out one at least, okay? So then we can figure out the other 2. So how are we going to solve for u and v here? So basically, this is something, I think there's a history behind it again. It's a classical problem in math. If you know the sum of 2 numbers and if you know their product, what are the numbers? So this comes down to solving a quadratic equation. So in this case, so this was historically known. If you, in this case, you know u cubed and v cubed, you know the product of u and v, so you know the product of u cubed and v cubed, right? And then you know the sum, so you can find what u and v are by this general methodology. So let's actually talk about it in this situation. So basically what we're going to do is we're going to first isolate one variable. So we're going to set that v is equal to p over 3u, right? Just dividing, looking at the first equation, v is equal to p over 3u. So now we're going to get that u cubed plus v cubed is q. So that's going to become u cubed plus p over 3u cubed is equal to q. So therefore, we're going to get that u cubed plus p cubed over 27u cubed is equal to q. Okay, so that's going to be our equation. We want to solve for u, and then we can figure out v by p over 3u. Okay, so that's what we're going to do. And now the trick is, whenever you have an equation like this, I don't like fractions. I mean, who likes fractions, right? You want to clear the denominators. Okay, so whenever you see a fraction in math, you're solving an equation, it helps to clear the denominators. So let's try to clear the denominators and see what that gives us. So that's going to give us something. So we multiply both sides of this equation by u cubed. Okay, so if we multiply both sides of this equation by u cubed, we're going to get that u power 6. So u power 6 plus multiply both sides of the equation by u cubed, so plus p cubed over 27 is equal to q times u cubed, right? And now, if we now make it an equation and you put everything to one side of the equation, we're going to get u to the 6 minus q u cubed plus p cubed over 27 is equal to 0. Okay, so this is going to be a 6th degree equation. Looks bad, okay, 6th degree equations. We started off with a 3rd degree equation. Now we have a 6th degree equation. So it looks like we've made our life harder, but actually if you've seen this trick, it's a very elegant trick. It's something it's worth knowing, whatever math you're doing. This is actually equivalent to solving a quadratic equation, because what we can do is we can change our variables. We can set, set y is equal to, I haven't used y yet, right? So set y is equal to u cubed, or maybe even w. That may be, let's set y, okay? Y is equal to u cubed. And then you notice this becomes y squared minus q times y plus p cubed over 27 is equal to 0. And this is a quadratic equation now. Okay, so the trick was that because it was a 6th degree equation but very special, you only had a 6th power and a 3rd power, you can get it down to this. Now we can solve for y using the quadratic formula. Okay, so the quadratic formula is going to tell us what y is. So I can actually erase this all off now. So let me erase this all off. We're going to solve for y. So y is going to equal to, using the quadratic formula, we know the quadratic formula. So y is going to equal to minus the second coefficient. So it's going to be plus q plus or minus the root of the second coefficient squared, which is q squared, minus 4 times the first coefficient times the third coefficient, which is minus 4p cubed over 27 divided, the whole thing divided by 2. Okay, so that's going to equal to y. And now what we can do actually is we can do a little trick. Okay, so this is going to be, so now you can sort of see, right? I'm just going to pause here. We've done it. Okay, there are going to be some small things to just comment on, but we've done it because we've solved for y. U cubed is y, so you can solve for u. And then we know what v is. V is going to be p over 3u. Then we just add u and v and we get our x. Okay, so we've done it. But let's just kind of just write it out nicely. Okay, so the first thing is I'm just going to factor out a 4 here. So this is going to be just a thing to simplify it. So I'm going to factor out a 4. So I'm going to write this as q plus or minus, I'm going to put q over 2 plus or minus the root of, so if you divide by 2, you're dividing by the root of 4. Okay, so we can say this is going to be q squared minus 4p cubed over 27 divided by 4. Okay, so I've just taken out the square root 4 inside, and now that's going to equal to q over 2 plus or minus the root of q squared over 4 minus p cubed over 27. Okay, so that's going to be our expression for y, and now we can figure out what u is. Okay, so u is the cube root of this, so I'm just going to erase this all off. So y is equal to u cubed, right? So u is going to be the cube root of this. So we're just going to now get that, I'm just going to erase this, we're going to get that u is equal to the cube root of this. So there are two solutions here. So u is going to equal to the cube root of, of this. So it's going to be cube root of q over 2 plus or minus the square root of q squared over 4 minus p cubed over 27. Okay. Now, quick comment is, what is v going to be, right? So v is going to depend on u. We can use this equation u cubed plus v cubed is q. Okay, so if u cubed is y, remember y was equal to u cubed, if it's that, then v cubed is q minus u cubed. Okay, so actually what happens is, so I'm just going to write this here, v cubed is going to equal to q minus u cubed, which is u cubed was y, so it's going to be q minus q over 2 plus or minus the square root of q squared over 4 minus p cubed over 27, which is going to equal to q over 2 minus plus. Okay, so when you take minus or plus minus, the signs are going to flip. So it's going to be minus plus the square root of q squared over 4 minus p cubed over 27. Okay, so minus plus is respective here. So if this was a plus, this would be a minus. And if this is a minus, this would be a plus. Okay, so that's all there is to that. So it's going to be that. And so therefore, v is going to equal to So I'm going to write it, it's going to be the cube root of this, right? Because v cubed is that, v is going to be the cube root of that. So let's just actually write that out. So v cubed is that. So we'll have a nice formula. V is going to be the cube root of this, okay? So v is going to be the cube root of this, which is going to equal to, so let's just write that out. V is going to equal to the cube root of q over 2 minus plus the square root of q squared over 4 minus p cubed over 27, okay? Now, here's the thing. Our x that we want in the end is just u plus v. Okay, so it doesn't matter if we choose u to be with this with the plus sign, v is going to be the thing with the minus sign. If we choose v to be the thing with the minus sign, u to be the thing with the minus sign, v is going to be the thing with the plus sign. Okay, because these are the same except the signs are flipped. So u plus v is always going to be the same no matter which sign we choose. So in other words, we can actually just, by symmetry, we can actually just choose one of the solutions. So we're just going to get plus and minus. Okay, so we can just say let u be this and let v be this. And that's going to be our u and v. So our x, our original solution to our depressed cubic, is going to be the following. Our x is just going to equal to u plus v. Okay, so it's going to equal to u plus v, because that's what we set our x to be in the beginning, which is going to equal to the cube root of q over 2 plus the square root of q squared over 4 minus p cubed over 27. And it's going to be plus the cube root of q over 2 minus the square root of q squared over 4 minus p cubed over 27. Okay, so that's going to be x, and that's going to be a solution to our depressed cubic. So a quick comment before I get into why it's sufficient to just solve this depressed cubic to solve any cubic equation, which is actually the easy part. Quick comment is, well, where are the three roots, right? You say that a cubic should have three solutions. So where are the three solutions and what's going on here? So the first comment is there is this quantity which we call the discriminant. You know, just like when you have a quadratic, right, you have a discriminant which is the b squared minus 4ac in the quadratic formula. Now, the sign of the discriminant determines what roots the quadratic has, right? If you think about the formula for a quadratic, so it's going to be minus b plus minus root b squared minus 4ac by 2a. If the thing inside the square root is negative, you'll have an imaginary, you'll have two complex roots. If the thing inside the square root is 0, you'll have one real root with multiplicity 2. Okay, so it's going to be one real root with multiplicity 2. That means it's just one root repeated twice. And if the thing inside the square root is positive, you'll have two real roots. Okay, so it's the same kind of idea here. This thing inside the square root here, right, it's the same thing in both cases. If it is positive, then you're going to have a real root for your depressed cubic. Okay, now that's going to be one root. How are you going to figure out the other roots? Well, the point is that a real number, right, whatever this expression is inside this cube root, it's going to be a real number. It's going to have three complex cube roots. Okay, so generally speaking, any number, if you take in the complex plane, so I'm going to go into complex numbers now, it's going to have three roots, okay, in the complex plane. So I won't talk in too much detail about that, but the idea is that to find the other roots of the depressed cubic, you want to choose the other cube roots accordingly. Okay, so you have three choices here and three choices here, right? So in theory, you could say that you have 9 choices. That's not right. There shouldn't be 9 roots to the equation. But you use the fact that 3uv is equal to p. Okay, so that actually narrows down the choice. If you choose one of the cube roots here, which is a complex number, your other cube root is actually forced by that equation 3uv equals p. So each of the choices of the cube root here, which are 3 different complex numbers, as long as the thing inside the square root is non-zero, each of those choices is going to give a unique choice for v. So you're going to have 3 different choices for u plus v. So you're going to get your 3 solutions to your cubic. So that is if the discriminant is positive, you can get like a real solution. If your thing is and you can get like one real solution just like this, and you can get the other solutions otherwise. If your discriminant is negative, you can do the same principle and you can get your 3 complex solutions. Okay, so in each case you can find the solutions from these 2 just by multiplying. So one thing is, if you have, I can just sort of write it down here. If you have, for example, if you're trying to solve an equation in the complex numbers, right? If you take a cube root of 1, okay, so omega is some complex number that cubes to be 1. If you know complex numbers, This is e to the 2 pi I over 3. And then you can take omega squared, that's also a cube root of 1, which is going to be e to the 4 pi I over 3. Then you can sort of multiply this cube root by omega and this one by omega squared, or you can multiply this by omega squared and this by omega. But either way, you can get the cube roots, or you can get all the solutions for x. Okay, so you can choose, this is u and this is v. You can multiply this by omega squared, this by omega squared, this by omega, or you can just leave it as it is, and you would get your 3 solutions. Okay, so that's kind of the process for finding out the solutions. There's a slight subtlety if u and v are, if this discriminant is positive. If the discriminant is negative, so the thing you're cube rooting is a complex number, you have to be a bit careful because these two things may not multiply. Depends on which cube root you choose. Okay, so if you have a real number, there's a natural choice of cube root, right? Every real number has a unique cube root. So you can choose that cube root for u and the cube root for v, and then you can multiply, as I said, by omega squared, or omega squared and omega. But if you have like these two are complex numbers, then you have to choose the appropriate cube root so they multiply to have that property that 3uv was p, which I wrote down earlier, and then you can get the 3 roots that way, okay? And there may be some repetition in the 3 roots. So that depends on the discriminant. Okay, so that's kind of a quick overview, but I'm going to maybe do another video on that, explaining that in more detail. But right now, let's just finalize by explaining why this suffices to solve any kind of cubic, even if it's not depressed. And I'm not sure why the terminology depressed cubic, but anyway, it sounds depressing. But the idea in general is if you have an equation x cubed plus ax squared plus bx plus c equals to 0, then what you can do is you can do what's called a change of variables to make it a depressed cubic. So how you do that is you're going to play around with it, okay? So the idea is this. Let's replace x by x plus a constant k. Okay, so x plus k cubed plus a times x plus k squared plus b times x plus k plus c equals to 0. Okay, k is a constant. Okay, so here's what you observe. Whatever solution for x you have in this equation, if you subtract k from that, you'll get a solution to this equation, right? If x is a solution here, x minus k plus k is just x. So basically, you'll go back to your original equation if you replace x by x minus k. Okay, so whatever solution x satisfies this red equation, subtract k, you'll get a solution here. So all your solutions here are going to be these solutions for the red equation subtracted by k. Okay, and so then what you have to do is just figure out a k so that you can get the x squared coefficient in this equation to be 0. And that's easy enough because if you expand this out again using the binomial theorem, you get x cubed plus 3x squared k plus 3xk squared plus k cubed plus ax squared plus 2axk plus k squared plus bx plus bk plus c equals 0. And you can group the terms, the like terms, the x coefficient, the x squared coefficient, the x cubed coefficient. So I'm just going to group, the x squared coefficients is to show you. The x squared coefficients is you're going to have a 3k there. So it's going to be 3k, and you're going to have an a here. Okay, those are the only x squared coefficients. You're going to have an a here, x squared plus dot dot dot. And you can choose k, okay? You choose your k, it's a constant. We're trying to figure out what is a nice choice. You choose the k so that 3k is a, minus a. Okay, so choose k. So the conclusion is choose k. I'm going to put it here. Choose k equals to minus a over 3. And then your new equation, once you've added k to x, is going to not have an x squared coefficient. In other words, it's going to become a depressed cubic for some p and q, which are going to be somewhat complicated expressions in terms of the original coefficients. So you then have to input this formula, the p and q. You have to find out what they will be in terms of the original a, b, and c to get the general formula there. Okay, I won't do that. That's a little messy and non-enlightening, but I encourage you to try. Drop me a comment down below. I'd love to see. Play around with it. Try to explain this to your friends and family. Share with your friends and family, how to solve a cubic. If someone knows how to solve a quadratic, they understand that. So I would say, if you know the quadratic formula, right, you don't even need to understand how to derive it. But ideally, you should understand that first before the cubic. But if you know what the quadratic formula is, you can understand this video. So share with your friends and family. I hope you love this video. As I said, a lot of people I'm pretty sure a lot of people doing math may not know this. It's not standard knowledge. It doesn't come up a lot, generally speaking anyway. It's not as important as a quadratic formula, but it's a beautiful derivation and it's a part of human history, that people found out you can find such a formula. You can also do it for fourth degree equations, but people got stuck when it comes down to fifth degree equations and higher. They couldn't find a formula. But it was proven by Abel and Galois, and that's another famous story, using this subject called Galois theory, which is somewhat advanced math, but very beautiful subject. Maybe I'll do videos on it in the future, where you can prove that you cannot find a general solution to fifth degree equations like we can sort of find here. You cannot find for fifth degree and higher equations using just simple arithmetic operations, roots, etc. You cannot do it. So that's amazing. People tried and failed, and then it was found out you cannot do it. Okay, so thank you so much for watching. I hope you loved that video. Please like, share, and subscribe. I love making it. It was a fun video. I sort of I knew about the overall idea here, but I just learned this kind of in detail and thought about it recently. Thought I'd do a video about it because it's fun to share. And I wish you all the best. I'm super excited to see you in the next video. Drop me a comment down below what the general formula is if you'd like to do that, or any questions or thoughts about this. Drop me a comment down below. I'd love to hear from you. So please do so, and I'll see you in the next video.